Here, we're going to learn a new technique for solving problems called related rates. So, suppose a spherical balloon is being inflated such that the volume is increasing at a rate of 2 inches cubed per second. We want to know when the radius hits 10 inches, how fast is the radius increasing? So the thing is, I know how the volume is increasing, but I don't know how much the radius is increasing. What we're going to do, kind of our highlight here, how we're going to do this related rates process is I'm going to take a formula that relates volume and radius, and then I'll use ideas from implicit differentiation to come up with a formula that not only relates volume and radius, but also the rate of change in volume and the rate of change in radius. Once I have a formula relating the rates of change, I can then solve for the current rate that I'm interested in. So let's go ahead and do some of that. So whenever you're doing a related rates problem, your first thing you're going to do is kind of split it up into a general situation and a specific moment in time. So our general situation would be asking the question, what's the volume? What's the volume of a sphere? Or more generally, what's a formula that relates the volume of a sphere to its radius? And we have that here. The volume of a sphere is given by 4/3 pi r cubed. Now we'll use implicit differentiation and I'm going to put that in quotes because we're actually going to do things a little bit differently to get a formula relating the rate of change in volume and the rate of change in radius. And how this is going to be different from implicit differentiation generally is that instead of taking the derivative in respect to r, which kind of what we did earlier is we had y's and x's and we said y is a function of x. So whenever we took the derivative of y, we had to put a little y prime, but whenever we took the derivative of x, it was just normal. What we're going to do here is we're going to say that all of my different variables are a function of some other variable t. So instead of only needing to put a little y prime whenever I take the derivative of y, I'm going to put a little dv dt or dr dt whenever I take the derivative. This also means that the product rule might show up a little bit more frequently. So it won't be a problem this time, but if I had like r times some other variable h, then I'd have to use the product rule when taking the implicit derivative there. But anyhow, so we're going to do the implicit derivative here. So on the left-hand side, I just have v, so I'm just going to rewrite it for clarity here. We have v equals 4/3 pi r cubed. On the left-hand side, we have v, that's just going to turn into dv dt equals 4/3 pi is all just some constant, so I'll just carry that down. But now I'm going to take the derivative of r cubed. So again, we're going to think implicit differentiation here. That's going to be 3r squared, but since r is actually just a function of t, I need to go ahead and multiply by the derivative of r in respect to t. You can think of that as using the chain rule. R was my inner function, so I had to multiply by the derivative of the inside. I can do a little bit more cleaning up here. We have dv dt equals, those 3's will just cancel, and it's going to be 4 pi r squared times dr dt. So now I have an equation relating my rates, which is why we might call it a related rates problem. Now that we have that equation, we're going to go to our specific moment in time. So what do we know about our specific moment in time? Well, we know that v is increasing at 2 inches cubed per second, and we know that our radius is 10 inches. So v is increasing at 2 inches squared per second, or 2 inches cubed per second. That means that the rate of change of v is going to be 2. We already have r. And what are we trying to find? We want to find how fast the radius is increasing. So how fast the radius is increasing that's just going to be dr dt. So what we can do is we can take our equation here and now plug in the values that we know. We know that dv dt equals 2. Then we have 4 pi. We know that r equals 10. And we're trying to solve for dr dt. We don't know that one yet. But it's not too bad to solve for it. All I need to do, let's rewrite this a little bit. We can write this as 2 equals 400 pi times dr dt. I just need to divide both sides by 400 pi. And what we'll get is that dr dt equals 2 over 400 pi inches per second. Looking at my units there, my rate of time is seconds and my length is inches. And of course, we can simplify that to 1 over 200 pi inches per second. That would be my answer. So this is one of the simpler related rates problems we can do. But as you see, we just set up a formula relating the volume and the radius. We then took the derivative to get us a formula relating the rates of change of the volume and the radius. And then we looked at my specific moment in time and plugged in specific values to help me calculate what the actual, or to solve for the rate of change of the radius. So there you go.